looks like it's only going to be on one screen.
All right. Hey everybody, welcome back. See a few more people done in the hands-on session. We're going to get going here. We're really fortunate to have Ka, who came here to give us a talk on GANs, and so he's going to take it away. Thanks a lot.
Thank you for the introduction. Okay, so in this lecture I'm going to talk about implicit general models, which is a broader class of general models that encompasses GANs and VAEs. So first I'm just going to go over the basics of general modeling and probabilistic modeling. So first of all, general models are simply models that can be used to generate data. And so to be able to generate new data, the model must be able to learn a distribution of data from finally many examples. And so this requires the model to be probabilistic, right? Because we want to learn some distribution. And so general models and probabilistic models are often used synonymously. So let me make the distinction between deterministic models and probabilistic models. So the simplest example for the deterministic model is a function that essentially takes in inputs and gives you an outputs, right? So here's an example of such a model, right? So we have linear regression. And so the function here is just going to be the dot product, right, between your parameters and your inputs. And so what's to know here is that for deterministic models, if you provide it with the same input, the output is always going to be the same, right? That's just a property of functions. And so in other words, these models can only give you point estimates, right? They cannot give you full distribution over the possible different outputs. So now let's take a look at probabilistic models, right? So probabilistic models are essentially a more general form of deterministic models where you can map the inputs x, right, to a distribution over the different possible outputs y hat. So in other words, we want to model the conditional distribution of the output given the inputs. And so here's a picture that illustrates this more concretely. Essentially, in the case of linear regression, we ideally want to also model the uncertainty, right, in the prediction. So for example, in kind of this part of the space, you want to say kind of the model is more uncertain just because your data points can have greater variance, whereas here you want to have less uncertainty. So ideally, you want to be able to model a distribution like this. And so, so that's where probabilistic models come in. And one of the major kinds of probabilistic models is what's known as implicit probabilistic models. So these are essentially models that are defined by some sampling procedure, right? So for example, in this case, we have this particular sampling procedure here that is essentially a determinist function with the original data, right, x as your input, as well as also this latent variable z, right, that's sampled randomly from some distribution p. And so in this case, right, so if you kind of keep the x fixed, and then if you were to draw random samples from the z, you can see that kind of this model is able to give you different outputs, right? And so this sampling procedure is implicitly defining some probability distribution over your output, right, given your input x. And so, right, so these kinds of models are characterized by the sampling procedure rather than some explicit specification of the probability density. We can also try to have probabilistic models that just model the conditional distribution over the y hat, right? So this corresponds to this picture where we ignore the x completely and just want to care about kind of modeling this marginal distribution over your outputs. And so we can also kind of define a corresponding implicit probabilistic model that essentially takes out the input x and then just have your z, right, as your only input. And so again, this is going to give you a distribution over the different outputs because that can be sampled randomly from some distribution. Any questions so far? Okay, good. All right, so now let's take a look at how do we actually learn such probabilistic models. So one of the most classic approaches, and it's also the basis for many more advanced methods, is the maximum likelihood estimation method. right? So the idea is that we want to find the parameters that maximize the likelihood function, which is also just the drawing probability of the observed data as a function of your parameters. And so here's what the objective is, and then essentially that's just a product of the different densities evaluated at the different data points, just because these data points are IID. And so that's known as the likelihood function, and then what we essentially want to find is some parameters that maximizes this likelihood function. So we want to find this parameter here, that's the maximum likelihood estimates. Okay, so let's take a look at a more concrete example of what this method penalizes, right? So this is an example where you achieve low likelihood, right? So these yellow points are your data points. And so if you have a model like this, it's gonna give you low likelihood just because these data points here have low density, right? Just because kind of your likelihood is a product of the densities evaluate all the different data points. If you just have one data point that has a near zero density, then the entire likelihood is going to be near zero, right? So that's essentially bad from the perspective of this objective function. And then what's good is something like this, where you kind of have high density, right, assigned to every one of these data points, right? And that's going to be something that the maximum likelihood estimator is going to find. Okay, so working with the likelihood function in practice is hard just because it's a product of the densities and we want to be able to turn it into a sum. So people generally just apply the log transform, right, which is a strictly increasing transformation, right? That's essentially going to preserve the softmax, right, as you can see, or the argmax as you can see in this picture. And so, essentially, kind of if you apply the log, then you are essentially maximizing likelihood is the same as maximizing the log likelihood. Okay, so let's briefly talk about KL divergence. So this is going to look like a bit of a digression, but as you'll see later, it's actually central to a lot of different general models. So KL divergence is just a way of measuring how different a distribution is from another distribution. And so this is the definition here. So the KL divergence from Q to P, right? So that's the same as the KL of P and Q, right? So notice the directionality here. So the KL divergence from Q to P is exactly kind of the expectation of your log of the ratio of your P, the density of P to the density of Q. So we have a couple important properties, right? So first we have non-negativity, right? So for any two distributions, the KL divergence is guaranteed to be non-negative, and it is zero if and only if you have kind of the two distributions being equal except for on the measure zero set. And finally, you have asymmetry, right? So in general, KL from Q to P is different from the KL from P to Q. So now let's do a little exercise just to highlight these points. Now we have two distributions here, right? So we have the blue curve and then we have the gold curve. And now I'm going to ask you this question, right? So which of these two things is larger? Is it the KL from blue to gold, or is it the KL from gold to blue? So how many people think it's the former? Okay, how many people think it's the latter? Okay, the rest of you are 50-50, I suppose. Right, so let's actually take a look. Essentially, now, we can kind of pick an example, right? So this is looking at kind of this point here, right, x naught, and then we're just going to look at what this term actually looked like at this point. So here we have, the gold distribution, right, evaluated at x naught, right? So that's a large value here. We're going to call that C. And then we have this inner ratio here, right? So this is actually exactly 2 times, right, the density of the blue curve, and so we get C times log of 2. Now let's take a look at this case, right? So we have now the ratio of the density of the blue curve, right, to the density of the gold curve, And so here again, right, it's just the reciprocal, so it's going to be a half. And then this point here is going to be c over 2, right? So that's what we're going to get. So, these two things aren't that, different. And so, this is kind of, an uninformative point that's not going to tell us much. But then if we are going to take a look at this point here, right, at x1, what are we going to get? So at x1, we are going to, again, evaluate this ratio here, right, gold to blue. And so you can see that at this point, like gold is close to 0, whereas blue is some positive number, right? So we basically get 0 here, right? That's, at least very small, very close to 0. And the gold curve here, again, that's going to be close to 0, so we're just going to get something like this. And then you can think of this as essentially being 0. And so let's take a look at this other KL, right, from gold to blue. And so now we see that if you take a look at kind of the blue over the gold, right, the blue is some positive number, whereas the gold is close to 0, right? So you're essentially dividing by 0, so you get infinity inside here. And then so you can see that this thing is just going to blow up, right? So at this point, the KL is just going to be, very large. And then so you can see that kind of, as long as you have kind of these regions here, right, you're always going to have kind of this sort of thing happening, right? And then, essentially that tells you that the KL, right, from gold to blue is this case infinite, whereas the KL from blue to gold is actually quite small. So this is actually the right answer. Any questions? Yes. Do you have a question?
Asymmetry of this measure, is that something that we need to be cautious about when we apply KL divergence?
Yes, that's basically what I'm going to talk about this lecture. So that's why I'm spending so much time on this, just because this is actually going to be very important. Okay. So the takeaway is the following, right? In order for the KL divergence to be finite, your P, right, which is your first argument, cannot be non-zero when the Q is 0, right? That's just going to make the ratio infinite. So in other words, the first argument, P, must be absolutely continuous with respect to Q. Okay, so now let's talk about what KL divergence actually means and try to gain an intuitive understanding of what it actually measures. So let's consider the following setting. We're going to draw n IID samples from some discrete distribution Q and consider the distribution of the samples, right? So the distributions of frequencies of kind of the sample attaining a certain value, right? So this is known as the empirical distribution. And so roughly speaking, the KL from Q to P is going to tell us how exponentially unlikely it is for this distribution of samples to be similar to P. And so think about that for a second, right? So essentially this means if we're going to take a look at the second argument, and then we're just going to draw random samples, and we take a look at the histogram, and the KL is essentially telling us, how likely is it for that histogram to seem like it's actually the same or very similar to your P, right, which is this first argument that you're comparing to. So this interpretation, which is due to Anand Sahai, is justified by a special case of what's known as the Synopsis theorem. And so this is the statement of the special case. And so what that is essentially saying is that if you take a large n, so you draw a lot of samples, then the probability that the distance, right, between your distribution of samples and the distribution that you're comparing to is going to be similar. The probability of those two distributions being similar is approximately going to be equal to e to the minus n times the KL from Q to P tilde, where P tilde is something that is similar to P, right, which is this target distribution that we're comparing against. So this tells us, why KL divergence is actually asymmetric, right? So here's a concrete example, right? So if we consider tossing a fair coin many times, there is a chance, albeit very small, that all the tosses are going to end up being heads, right? So this says the KL from a fair coin to a coin with heads on both sides is going to be finite, right? There is a very small chance for that to happen. On the other hand, if you toss a coin with heads on both sides many times, then it is just not possible for a tail to appear, right, in any of the tosses, just because there is no tail, right? So it's not possible for the tosses to resemble the distribution of outcomes for a fair coin. So that tells you that the KL from the coins with heads on both sides is to the fair coin is going to be infinite, right? No matter how hard you try, you're never actually going to have a non-zero probability of the sampling distribution coinciding with the distribution that you're comparing to. Okay, and there's a connection, of course, between maximum likelihood and the KL divergence. So maximum likelihood is equivalent to minimizing the KL divergence from the model distribution to the empirical data distribution. So this is essentially what it says here, right, in this equation. And so how do we actually remember the direction, right? So how do we remember that it's the KL from the model to the empirical data distribution rather than the other way around? So if we recall the previous interpretation of the KL divergence, which would be always drawing samples, right, from the model. We should never be drawing samples from the empirical data distribution because that doesn't actually make much sense. We should be drawing samples from the model and then we can compare the distribution of the samples to the data that we actually observe. Any questions so far? Yes. Yes. Okay, total variation distance. So this you can think of as essentially the L1 distance between either the probability mass function of, if in the case of the discrete distribution. So it's essentially just taking the absolute values between kind of the difference in the densities at every point.
So here you assume P to be also discrete, right?
Sorry?
You assume P also to be discrete here?
In this case, yes. Yeah, P and Q have to be discrete. So you could extend it to the continuous case. The state of the theorem is going to be more complicated. But essentially the way you can extend it is by essentially thinking about all the possible discretizations of a continuous distribution and then taking essentially the infimum, right, over all the possible discretizations. So that's going to give you the continuous KL from just discrete KL. Okay. Now let's talk about variational autoencoders. So you've seen this yesterday briefly, and then I'm going to give a slightly different perspective today. So variational autoencoders are defined in terms of the following sampling procedure, right? So remember here we're viewing variational autoencoders as an implicit probabilistic model. So these models are defined, right, by a sampling procedure, and so that's just the definition of, what the model actually looks like. So essentially it's something like this, and here's the picture that shows you kind of what this equation says. So we're going to take in, right, some random variable z, right, that's the latent variable, and then we're going to feed it in, right, to a neural network. And so one branch of the neural net is going to take that latent vector and give you the mean, right, of the distribution, right, on the outputs. The other branch is going to take the input, right, and give you the standard deviation, right, so that's this picture here. And then finally you have another latent vector, right, that's z prime, right, that's essentially going to be the source of randomness, right, at the observation level. So you're going to multiply that, right, with the standard deviation that you've learned, and then add it, right, to the mean, right, to give you the final output, right. And so that's essentially what this equation says here, right? So you have the mean, you have the standard deviation, you're going to add them together. And so, right, so this is essentially how the model is defined from our perspective. And so let's think about how do we actually learn this model, right? So, the simplest thing we can try is to actually maximize likelihoods, right? And so let's try to maximum likelihood, right? So this is the objective, right, of maximum likelihood. And then, right, so this thing here, right, just kind of to give you the kind of the terminology. So this is typically known as the marginal likelihood or just the likelihood. So this, by the way, is different from the likelihood function, right, which is defined as the product, right, over all the likelihoods, right, associated with each data point, right. So this, each individual data points, just the marginal probability is known as the marginal likelihood or the likelihood. And we're going to apply Bayes' rule, right, to decompose this, right. So the log likelihood here, right, is going to be essentially, just the same as the log of the complete likelihood. So this is known as the complete likelihood. And then you're going to marginalize, right, out your latent variable z, which can be further decomposed, right, by Bayes' rule into the prior and the conditional likelihoods. So in the case of the VAE, our z, right, is going to come from a standard Gaussian. And the conditional likelihoods, right, which is the y hat, right, the observation given the latent variable, is going to be another Gaussian with mean of f theta mu, right? This is the one branch of the neural net, right, that outputs the mean. And then we have the covariance, right, being equal to essentially, this quantity here, right, which is just the the kind of the square. You have the diagonal matrix where each entry on the diagonal is going to be the squares, right, of the entry, right, that you predict, right, in your standard deviation vector, right, from the neural net. And so this, you can see this by just basically thinking about where the randomness actually comes from, right? So if you're given your z, right, so these two things are going to be fixed, right? So the only source of randomness left is this z prime. And so this essentially amounts to scaling and shifting the distribution of z prime, right, which initially was just a standard Gaussian. So if you were to apply this transformation, then you just get the means and the covariances here. Okay, so let's try to actually compute this quantity, so what that actually looks like. So if you were to write it out, it's going to look something like this. So there's an integral, right, over here that's kind of integrating over all the possible values of your latent variable z. And the thing to note here is that this is an integral that's difficult to evaluate, right? So you can't really hope to integrate this analytically just because your neural nets is actually in here, and then that's going to make the whole expression very complicated. It's also intractable to compute numerically. So that just tells us that we cannot actually use maximum likelihoods, right, just because we cannot actually marginalize, right, over the latent variables, right, in the complete likelihoods. And so, we have to try to work around this. And so variational inference is a method of doing so. So the key idea is that instead of computing the marginal likelihood directly, we're going to make use of this identity here. And so let's see, so the first step is, so we're going to essentially rewrite this, right, as an expectation. So the expectation here, right, is going to be taken over the posterior, right? And so just because z actually doesn't appear in this expression, obviously the two things are equal. Next step, we are going to replace this, right, with a ratio, right, of the complete likelihood to the posterior. So this is just by applying Bayes' rule. And then, so now let's take a look at this quantity here, right? So stare at this for a second. And so what's nice about this is now we have this thing here, right, which is the complete likelihood. And that's very easy to compute, right? Because there's no integral anywhere, right? There's no marginalization that we need to do, right? So this is easy to compute. Now the problem is that in the denominator, right, we have the posterior, and the posterior does involve marginalization over the z. And then so you get this expression out. Again, you have this integral here, but we don't really know how to compute this, right? So that's not really a feasible way to actually solve this problem. So what can we actually do here, right? So, we have this nice transformation that kind of made one part of the problem easier, but the other part as hard, so we didn't actually get anywhere. So what do we, yes?
In the previous slide,
Yes.
you had a diagonal vector and multiplying.
Yes.
Is that an outer product or is it just a square?
No, it's two square matrices, right? So diagonal, it means you have the entries right on the diagonal, and then so it's two.
What do you need to transpose?
Oh, it's just to, I mean, this is kind of, okay, this is not non-simplified form, right? So, if you actually write out like what the covariance is actually going to look like, this is supposed to be kind of what you're supposed to do, right? If you don't have diagonal matrices here, right, then that is what you're supposed to do.
Diagonal is square, I see.
You could, yes. This is just to make things explicit so that people know kind of it's this transpose rather than the other transpose. But this is a minor technical point. Okay. Let's see. Right, this is hard to compute. Now, let's do some wishful thinking here and think about what if we actually don't have this problem, right? So we can just kind of wouldn't it be nice if this were easy to compute? And let's actually make that happen. So what do? We're just going to replace it with some other distribution. So Q, right, that's going to take in your output y hat, and then it's going to give you a distribution over the z. Now this family of distributions Q is known as the variational family or the approximate posterior. So how is this quantity here, this new quantity, where we replaced the denominator with Q related to the original objective? So let's take a look at the approximation error, right? So, this is the approximation error. We're going to take a look at, how different they are. And so let's try to, derive this. So first step, we are going to, again, replace this thing with an expectation, right? So using the same logic as before, right? It doesn't actually matter where, which distribution the z actually comes from. Because the z doesn't actually appear in this expression. And so next step, we're going to use the linearity of expectations and then essentially move that thing inside, right? So we just have kind of the difference between these two, taken with respect to this distribution. And then finally, we're just going to use the property of logs, right, to essentially transform this, right, into a ratio, right, of this thing multiplied by that thing divided by this thing, right, just because this minus you can move it inside. And then finally we can apply base rule, right? So this is essentially saying, right, so we have the ratio, right, between kind of the marginal distribution and the complete log likelihoods. And then so we can essentially transform that to your posterior. And so does this actually look familiar, this last expression? Yeah, that's the KL divergence, right? So it's the KL divergence from the true posterior, right, to this approximate posterior. Okay, so the takeaway is the following, right? So the approximation error is going to be exactly the KL, right, from the true posterior to the approximate posterior. And so we can essentially view, kind of, essentially move this thing, right, to the other side of the equation. And essentially interpret this as a decomposition, right, of the log marginal likelihoods, right, into two terms. One of which is this, this imaginary quantity that we came up with, and then this KL term. And so we know that the KL divergence is always non-negative, and so this is essentially always going to be a lower bound on your log marginal likelihoods. And so, and this is what's known as, okay, so right, so this is, the KL can be essentially interpreted as the gap, right, between this lower bound and the true objective. And so this quantity here is known as the variation lower bound, or the evidence lower bounds, or ELBO for short. Okay, so let's take a look at the implications, right? So, earlier we talked about the directionality of KL, right? So, so it's really important to pay attention, right, which direction this thing goes. So it's from the true posterior to the approximate posterior. And so what are the implications? And so here's a picture that shows you kind of the implications. So this red curve here is the true log likelihoods, whereas this purple curve here is the variational lower bound. And then this gap, right, between kind of these two curves is just going to be your KL, right, from the true posterior to the approximate posterior. And so let's consider kind of 2 points, right, in the parameter space. At this point here, essentially you have a large KL, right? A large KL from the true posterior to the approximate posterior. So that's what's happened, right, if you have something like this. So here, the blue curve, right, is going to correspond to your true posterior, and the gold curve is going to correspond to your approximate posterior. And so if your approximate posterior cannot actually model, right, sharp distributions, then you'll essentially end up with kind of an overly broad distribution. And now if you remember, right, so just because kind of P is going to be on the right-hand side, P is going to be in the denominator, Q is going to be in the numerator inside the log, right? And then at these points here, right, where the blue curve, right, is near 0, but the gold curve isn't, that's going to make your KL blow up, right? So this is going to lead to a large KL divergence. That means a very loose lower bound, right? Whereas at this other point here, you're going to have a tighter lower bound, right? So you have a smaller KL divergence, and this is the situation when your true posterior is actually quite broad, and then your approximate posterior can actually, can model kind of some modes of the true posterior, the distribution of the true posterior. And so, this sort of bias, right, is basically what leads to your approximate posterior being kind of, not very, or being the parameters that you estimate being biased against, where the posterior is actually sharp, so you would actually prefer, right, kind of location of parameter space where the true posterior is not very informative. And so in the literature, this is sometimes known as posterior collapse. Any questions? Yes. Yes, you certainly could. The only issue there is just kind of if you were to write it out, right, you basically need to essentially think about how to actually estimate the parameters of the Gaussian mixture model, right? So typically you would use EM for that, right? But then kind of this EM is kind of in their inner loop, right, of kind of every step of fitting kind of the other parameters, right, of your true model, right? So then kind of it's just kind of a more involved optimization procedure involving optimizing the parameters of your model, right, and then optimizing your variational parameters. Yes? Right. Yeah. Right. Right. I mean, so if you do know something about what the true posterior looks like, right, definitely it is better to choose a variational family that tries to match, right, that. But the problem is basically the reason why we're using variational inference is because exactly we don't know what the true posterior is, right? So it's kind of, an arbitrary choice in practice, right? You choose some, variational family that's convenient mathematically, but, theoretically, sure, it would be nicer, right, if you were to choose something that actually, is close to the distribution of posteriors, right? In fact, if your variational family actually contains your true posterior, then this is actually going to give you exact maximum likelihoods, right? So it's the best possible thing you can hope for, but then again, in general, that's possible just because we don't know what the true posterior looks like. Yes?
Because we also learned only the positional distribution on the latent.
Right. Right. I mean, yeah, so I'm not sure what your question is. So we're fine with a Gaussian approximate posterior just because what? Right.
very well.
Yes.
Couldn't the conditional distribution in the set adapt to that mismatch?
The distribution given the sets. What that? Okay, maybe we can take this offline. I'm not sure.
The decoder learns to be such that the posterior process is actually exact.
Oh, right. If you choose a flexible enough variational family, then yes. Okay, so let's take a look at some empirical results of the latest version of VAEs. So this is VCO VAE. Obviously, very impressive. So these are very high-res images, and you can see they're, you can't really tell them apart from real images. Okay, now let's move on to GANs, general adversarial nets. So here, in the case of the GAN, the model is simpler, right, than the model used in the variational autoencoder, right? So we just have a input latent variable z, right, that's essentially going to be fed in, right, to this deterministic transformation, that's the neural net, and then that's going to give us our sample, right, y hat. Now, if you compare that to a VAE, right, so we essentially kind of remove this extra term, right, that's essentially, modeling kind of the variance, right, in the observation space. So in the case of the GAN, we're assuming that there is no observation noise, and then essentially your function, right, the only source of randomness, right, is your input latent variable. You don't have any extra source of randomness that's added on, right, to your mean, right, in the case of the VAE. Okay, so now let's see how to actually learn the parameters of a GAN, right? So can we use variational inference, right? So recall we need to compute the variational lower bounds, right, which looks like the following, right? So we have the complete likelihoods, right, on the top, and then we have the approximate posterior on the bottom. And so let's try to write down what the complete likelihood for a GAN actually is. So we're gonna again apply Bayes' rule, right? And then we're going to have something of this sort, right? So we have the same prior distribution as before, right? So this is just a distribution of standard Gaussian. And then just because this is now deterministic, right? So given the z, we actually know exactly what y hat is. So there's no randomness in here at all. So we're just going to end up with a delta, right? And what the delta is, for those of you who don't know, is essentially this generalization of a function where essentially you have infinity, right, as 0 and 0 everywhere else. And so you define it such that kind of if you integrate over the entire domain, you're going to end up with 1. And so this is essentially saying that we're only going to have a non-zero density, right, when the y hat is exactly equal to what your active model actually gives you. Now let's compare that to a VAE, right? So in the case of the VAE, right, so we have, again, the complete likelihoods, and then so the prior is going to stay the same, and the conditional likelihood, right, is a Gaussian, and so we have this, right, instead of that. Now this is problematic in the case of the GAN because the delta, right, cannot actually be evaluated, right? It's not even well defined. Technically speaking, that's not a function, right? So so we can't actually compute this at all. So that just means we cannot use variational inference. So we have to use another class of methods known as likelihood inference, right? So that just means we have to learn a model without being able to compute even the complete likelihood or any derived quantities, and this is known as likelihood inference. So in the case of the GAN, the key idea is to introduce a classifier known as a discriminator that's going to distinguish between your real data and the generated samples. Now, we're going to train the model, right, which is known as a generator in the GAN parlance, so that the generated samples are misclassified by the discriminator, and then we're just going to alternate between training the discriminator and the generator. Okay, so here's a picture of a two-dimensional data set that kind of illustrates how GAN training works. Here, the red squares are the real data examples. The blue circles are the generated samples. And then, so in the first step, we're going to train the discriminator. So for simplicity, in this case, I'm showing one nearest neighbor classifier, right? So it has this decision boundary here. And so the yellow regions are the regions where the discriminator thinks things are real, and the white regions are where it thinks things are fake. And so after we train the discriminator, right, we're going to train the generator, right? So that's essentially amounts to pushing, right, all these samples towards the yellow regions, the real regions. And then after we train the generator, we're essentially going to retrain the discriminator, right? So we get a new decision boundary. And then we're going to train the generator again, right, which involves, again, pushing, right, all these blue samples towards the yellow regions. And so that's what we get after 2 iterations. So the objective function in the GAN looks like the following. So, so let's try to parse this a bit, right? So inside here, right, this is simply just the negative cross entropy loss, right? So what it's saying is, so this phi here is the parameters for your discriminator. So the discriminator, you're going to try to essentially maximize the negative cross entropy, right? Which is to say you want to kind of have the prediction or classification be as accurate as possible. And in the other loop, you have the minimization, right, over the theta. The theta is the parameters for your generator or your model. And then you essentially want to find the parameters, right, and then kind of minimize the classification accuracy. And so GANs are optimized using stochastic gradient ascent and descent. And so essentially, more concretely, what we do is we're going to draw samples, right, from the standard normal distribution. So that's the power distribution, and then we're just going to kind of alternate between kind of these steps, right? So we're going to first ascend, right, in theta, right? So that's the parameters of the generator, and then we ascend in the parameters of the discriminator. Okay, so gradient ascent descent is guaranteed to converge in the concave convex setting, right? So what that means is for an objective that is concave, right, in the phi, right? So concave in the discriminator parameters, and convex in the theta, right? So convex in the generator parameters, then gradient ascent descent is guaranteed to converge. However, in general, may not, which could cause training to be unstable. So here's a simple toy example, right, that shows you kind of why it may not converge, right? So, so these arrows here, you can think of that as kind of the updates that you're performing, right, in GAN training. And so you can essentially end up with this situation, right? You can kind of go around and around in circles, right, and you never get to kind of where you want to get to, right, which is this point here. And so these GANs produce amazing results, right? So, so these are kind of, again, the latest version, right, of GAN, which is known as big GAN, and then they produce, very nice looking pictures. Okay, so let's think about how this actually relates to probability densities. So it is still somewhat of an open question. I'm going to talk about why in a second. So in the original GAN paper, right, so there's this optimal discrimination result, right, which essentially says if if you want to look for a discriminator that is the optimal, then it essentially looks like the following, right? So you have the true data distribution, right? The density of the true data distribution divided by the density of the true data distribution plus the density of your model. And so given this result, we can rewrite the GAN objective as minimizing this objective, right? So this thing here is the KL, right, from the average of the two distribution, the true data distribution and the model, to the true data distribution. And then, again, we have the average from the average to the model distribution. So this thing here is what's known as the Jensen-Shannon divergence. And so the reason why I'm saying it's still somewhat of an open question is because this result relies on two different assumptions. So the first is that we have to have access to the true data distribution, T data, right, rather than just the empirical data distribution, right? And secondly, okay, so right, this kind of shows you, kind of what this looks like, right? So, for the true data distribution, right, obviously we have kind of this well-defined optimal discriminator, but then if we were to just have an empirical data distribution, right, the optimal discriminator is no longer well-defined. And also we have to have an infinitely expressive discriminator that can model any function. And so relying these assumptions is tricky because of the following. So these two assumptions are kind of at odds with one another, right? So, if you only have access to a finite data set, right, then you need the discriminator to generalize, right, to unseen data. For that to happen, you need to limit the capacity of your discriminator. But then if you were to limit the capacity, then, it cannot be infinitely expressive. And so, this is a question that, some recent papers have begun to look at, but, it's still a very much open question. Okay, so GANs suffer from this well-known issue known as mode collapse. And so I'm going to illustrate, what that looks like, right, in this two-dimensional picture that I had earlier. So if you pay attention, right, there are kind of these data points, right, these red squares here, that don't have any blue points nearby, right? So the blue points are the generated sample, and then if your generator cannot generate something that is close to these real data examples, then that effectively means it's assigning low density, right, to these data points, and these are the models that are being dropped. And so the learn generator may not be actually able to generate some data points, so they're effectively ignored. And so that's kind of, what mode collapse means. And now let's think about why mode collapse actually happens. So the GAN objective that's used in practice minimizes the following. So this is a result from this paper here that shows that it's minimizing the reverse KL, right? So that means that KL from the data, true data distribution to the model, minus 2 times the Jensen-Shannon divergence. So the Jensen-Shannon divergence is bounded, right? It's bounded from between 0 and log 2. So we can expect to ignore this quantity here, just because this is a term that's going to dominate. Now, maximum likelihood is equivalent to minimizing the KL from the model to the empirical data distribution, right? That's what we saw earlier. And so essentially, GANs are minimizing KL in the opposite direction, right? And so this is known as reverse KL, right? So it's the reverse KL is from the true data distribution to the model, whereas the forward KL, right, is from the model to either the empirical data distribution or the true data distribution. So let's take a look at the behaviors of forward versus reverse KL, right? So if we try to minimize forward KL, right? So we have kind of this picture here. So the true data distribution here is shown by the blue curve, and the gold curve is the distribution that minimizes the KL divergence from the model to the true data distribution, right? So that turns out to be this curve here. And so the way we make sense of this is that now by taking a look at the definition, right, we're going to pay a high penalty if if we assign low density, right, to dense regions of the true data distribution, right? So that means for every kind of mode, right, in the true distribution, we have to cover that, right, with our learned model, right? Otherwise, the KL from the model to the data distribution is actually going to be high. So this is mode coverage, right? It's going to try to cover all the modes. So whereas for reverse KL, kind of the opposite thing happens, right? So the ratio again now is reversed, right? So now we have the model density, right, over the data density. So this essentially says we're going to pay a high cost if we assign high density, right, to sparse regions of the true data distribution, right? So if there's some region in the true data distribution that doesn't actually occur, and then if our model actually assigns high density to that region, then we're going to pay a huge penalty. So that essentially means that we better be conservative and only kind of model, kind of the modes that are kind of we're sure about, right? So in this case, we're just going to kind of model this mode here, and then kind of non-model this other mode of different data distribution. Any questions so far? Okay. Right, so this is mode seeking, right? So you're going to be seeking, right, particular modes to cover. Okay, so let's think about this in terms of precision and recall, right? So this is another perspective of kind of what I just said previously. So precision in this case can be thought of as essentially a measure of how many generated samples look real. And recall is kind of the opposite, right? So how many real data examples can be actually generated? And so let's take a look at kind of the difference, right, between forward KL and reverse KL in this setting. So for a given model, if we minimize forward KL, that's going to prioritize recall over precision, right? Because it's going to try to cover all the modes. It doesn't care if it generates spurious modes. On the other hand, minimizing reverse KL is going to prioritize precision over recall, right? It wants to get all the things that you model exactly right. It doesn't care about ignoring some modes of the true data distribution, right? So that's kind of shown in these two pictures here, right? So forward KL, that's kind of achieving high recall, low precision. Reverse KL is low recall, high precision. So which of these things is actually better? So I would argue that from a practical standpoint, prioritizing the recall or minimizing forward KL is actually better. So why is that? Is because in the outer loop, right, that's typically the human researcher, right, tuning the architecture and the hyperparameters. So we tune the architecture, right, to obtain good performance, right? And then if it doesn't, then we're just going to change the architecture. So it's relatively easy to humans to gauge precision, right? So we can just generate a bunch of samples and look at them and see if they look nice. It's harder, right, for us to gauge recall, right? It's just not humanly possible to go over say millions of examples and see whether that actually spans the entire distribution. So, so if the model optimizes for recall, right, then if we in the other loop optimize for precision, then we can hopefully obtain a higher precision recall curve at the end, right? So hopefully we can achieve something like this. So initially maybe we're here, but because the model is making sure that you have high recall, and then we are making sure that we have high precision, we hopefully essentially shift the curve up, right, to achieve high precision and high precision at all levels of recall. On the other hand, if the model optimizes for precision, then and we optimize for precision, right? So both the model and the researcher are looking for kind of sample quality, right? Then we can end up kind of just moving along the same precision recall curve, right, without ever kind of having a chance to actually shift this thing up, right? Because we never know, what the level of recall is actually like. Question? Yes.
So if we push our model to the highest precision point, are we then going to generate the exact data without any different samples?
Oh, okay, right. So you're saying, what if we were to get to this point where we just have a single sample, and then you're saying, what if we then optimize for recall?
Yes. No, I'm saying we just make it get highest precision. That's equal to just caring about having a good quality image regardless of which figure it is. So mine might collapse to one of the
Right, yeah. So that's kind of this point here, right? So if you have very low recall and high precision, right, that's essentially generating this one sample, but really. Yes.
How can we evaluate the multi-story power as well as video quality at the same time? Because when you're iterating, you have the right classifier to have the adversarial classifier. How can you rely on the evaluation measure?
Right.
Yeah.
Yeah.
And I'm not talking about like compiling data sets that are specifically for multi.
Right. So I mean, okay, so there's like a couple of different approaches. And let me get to this question first. Oh, okay, sure. Oh, the question was, so what if, sorry. I think, okay, can you repeat your question? Oh, okay, right. Okay, right. Okay, right.
One way is to rely on the second is the data sets that are compiled out of more.
Right.
You cannot get one render.
Okay, right.
Because of the existence of adversarial, you rely on the classifiers for
Sure.
how many
Yeah.
classes you can solve.
Okay. Right, so the question was how do we actually evaluate recall, right? So for precision, it's easy because you can have kind of, take a look at the exception score of FID, right, which essentially looks like how well example classifier, right? But for recall, it's harder, right? Because it's kind of, you can always have a classifier, and we know that there are adversarial examples, so, it's not a reliable indicator, right, of, actually, like how well it's doing, right? So is that right? Okay. Right. So I think right. So that's that's a good point, right? So I guess right now what people are doing, right, is that typically for evaluating recall, right, we aren't actually using a classifier, and instead we're kind of using some sort of decimal metric that's predefined. Now, granted, the decimal metrics are usually operating on top of some other trained neural nets, right, that's trained on some auxiliary task, right? So, for example, kind of you would take a neural net trained on image, and then you would extract features, right, for those images, and then you compute distances in the feature space, right? It's not the ideal solution, right? There should be a better one. It's just that people haven't really come up with a metric that's kind of measure similarity, right, between kind of different examples of the same domain, in terms of
We can do separate the activation of each class and then compute the distance between the activation of class 1 data and the activation of generated from class 1 data.
Right. So yeah, so that's kind of limiting yourself to the classes, right? So it's so you can imagine kind of you can have recall in each of the classes. Right? So maybe like in each class you have relatively good diversity, right? If you just were to group things by classes, right? But then if you were to group things along some other dimension, like maybe it's not diversity, maybe it's not diversity along that dimension. So this is kind of you're kind of restricting yourself to just looking at diversity either across the classes, right, or just doing kind of a simple variance computation within the class, right? But then it's possible that kind of along some dimension, I don't know, like say for example, right, in your data set you have different object categories and then you have different backgrounds also, right? So maybe for the different object categories, right, you are achieving the diversity, but then you aren't achieving diversity in terms of kind of the backgrounds, right? Like whether it's in-dual or out-dual or sunny or rainy, right? Just because you don't have labels for those attributes, right, you don't know how diverse that actually is. So it's also kind of, just relying on class labels isn't really a good or satisfying solution. Yes?
So you can estimate entropy as not with the generator.
Right, yeah. Yeah, so the issue there is estimated entropy.
So you can only use adversarial.
You could, yes. And then you kind of get into the issue of evaluating something using the same method as what your model actually is.
It's going to be a different.
It's a different network, yes. Right. So among the two methods that we discussed, right, so VAEs and GANs, right, so there are pros and cons, right, for each, right, so for VAEs, right, it's not like it's free, right, so we do need to know what the company likelihood actually is, right, in order to use it, but it does have more coverage, right, so just because it's maximizing the lower bound on the log likelihoods, you're going to cover kind of all the different modes of your distribution. For the GAN, right, it's kind of the opposite situation, right? So it's likelihood free, right? So you don't need to know what the company likelihood actually is. You don't need the expression for it at all, right? All you need is the sampling procedure. And on the downside, it is that just because it's optimizing reverse scale, right, you can be modeling a subset of the modes and not the full distribution. Now, can we actually get the best of both worlds? And yes, we actually can. And so I'm going to talk about this other method that we developed, I guess, last year, called implicit max likelihood estimation. And then that's hoped to kind of address both of these issues, right? It's both likelihood free, and it also covers all the modes. Okay. So the model we're going to consider is the same as the generator and the GANs, right? So just to remind you, we're going to draw some random vector, right, from a Gaussian, and then we're going to pass it through a deterministic transformation to obtain our sample. Now let's take a look at again, right, how GANs behave. So again, the red squares here are the real data examples. Blue circles are the generated samples. And now I'm going to ask you to pay attention, right, to how the blue circles are actually going to move. So so first up, right, we train the discriminator, and then we train the generator, and then we train the generator, and then we train the discriminator, and then we train the generator, right? So that's basically what happens. And then, obviously, you see kind of these data points that are dropped. So what actually went wrong here? So essentially, each generated sample is pushed, right, towards the nearest data example, right? That's basically what it did. So this makes sure that each generated sample has a nearby data example. But what it doesn't ensure is that each data example has a nearby generated sample, right? So notice that we flipped the direction here, right? So we're saying around, kind of previously around every blue point, right, we have some nearby red square. But then it doesn't make sure that around every red square we have some blue circle. And so that's why modes are being dropped, right? It's because kind of you have these data points that are in some sense not being selected, right, by any of the samples. So how do we actually fix this? It's actually really simple, right? So we're just going to do things the other way around. So that is, each data example will now pull the closest generated sample towards it. And that's the basic idea behind our method. So let's take a look at a more concrete illustration. So again, we have the same data set as before, and just to remind you, red squares are the real data examples, blue circles are the generated samples. And so in the first step, we're going to look around, right, every real data example and find the nearest generated sample. And so these are the nearest sample, right, to each of the different data points here. And then we're just going to optimize the parameters of our model, right, so that these nearest samples are pulled, right, closer, right, to the data examples. And then we're going to do that simultaneously, right, for all the different data examples. And that's it. So it's really simple, right? So this is the objective function that we have. And so let's try to parse this. So in the first step, we're going to be essentially trying to find a minimum distance, right, over kind of all the different possible generated samples, right, to the current data example yi, right? So this is going to go over all the different z's, right, the random vectors that we generate. We're going to get the samples out, and then we're going to look and see which one's the closest, right, to yi. So this, by the way, right, involves high-dimensional nearest neighbor search, right, because these things could be very high-dimensional, which could be hard, right, due to the curse of dimensionality. Now, fortunately, this is no longer an issue, and this is applied for one of my other papers. And so, we can use this method called DCI, which I developed like a few years back, that overcomes inclusive dimensionality, actually. So we can actually show the runtime has no exponential dependence on the ambient or the intrinsic dimensionality. So, if people ever tell you that you can't really do nearest neighbor search in a high-dimensional space, that's no longer true. And okay, next up, we're going to average over all the real data examples, right? So this is again kind of the nearest, the distance to the nearest sample, and then we're going to do that right for each of the different data examples. And finally, we're going to take the expectation over the different generated samples, right? Just because the samples are random, and then we want to kind of minimize the mean right over the possible different generations. And we're just going to optimize using ordinary stochastic gradient descent, right? So this is also easier than kind of the case of GANs, just because we no longer need to do gradient descent, right? And just use ordinary gradient descent just because it's a simple minimization problem, right? And so what do we do actually, right? So we're going to sample the latent vectors, right, from a Gaussian, and then we're just going to do standard, right, gradient updates. Okay, so what is the connection to maximum likeliness? So this is a very rough intuition. So if you think about a model distribution that actually maximizes likelihood, then it should have high density at each of the data examples, as I've shown before, right? Because you want to make sure that all the different data examples in the data set are actually covered, right? They have high density. And so if you were to sample from the model, then the sample is going to be more likely to lie near a data points than elsewhere. So intuitively, to maximum likelihood, we simply want to kind of make sure that this actually happens, right? So we want to make sure that at every data point, we have some nearby general sample. And so this is kind of a bit more precise result, but still informal. The precise list of conditions is inside this paper. But essentially what that says is if the model is usually parameterized and the density is smooth in both the parameters and the data, then essentially if you were to minimize the analytic objective, then that is the same as or equivalent to maximizing a lower bound of the log likelihoods. So this is the lower bound, just because WI is some number from 0 to 1. And the way that the WIs actually depend on your model is that the tightness rate of this bound is going to depend on the gap between, so the maximum density rate assigned to any data point at the maximum likelihood solution, and the minimum density rate assigned to a data point at the maximum likelihood solution. So you can imagine that if you have a very regressive model, then it's kind of, the model would prefer assigning roughly similar density, right, to all the different data points, right, to maximize the product, right, of the different densities, and so the tighter that bound becomes. Okay, so let's take a look at some empirical results here. So this is looking at kind of the F measure, right, which is the harmonic mean between the precision and recall. And so this on the horizontal axis, you see kind of the number of hyperparameter settings that you tried, right? So this is a hyperparameter training budget. And so these different curves here all correspond to different variants of GANs. So as you can see, the more hyperparameter settings you, the more time you spend on tuning hyperparameters, you get better and better performance. And this here, right, the red dot here, that is our method, right, so that's FMLE. And so you can see that, so in this case, we didn't actually try tuning hyperparameters at all. This is literally the first thing that we tried. And it's already achieving an F score that is much better than kind of all the different variants of GANs. So let's take a look at some applications, right, to conditional image synthesis. So the reason why we're looking at conditional image synthesis is because in this case, right, mode collapse is more apparent, right, because in the training data, right, for each impulse, we only have one ground truth output, right? So if the mode collapse is actually happening, it's actually going to collapse all the generative samples right onto kind of a single data point. And so here you can see that this is the passive super resolution, which basically means going from a low res input to a high resolution image. And so here you can see kind of the different samples that we generate, right, conditioned on the same input image. Whereas this is SRN, which is a GAN that's with an architecture that's designed for super resolution. And then you see kind of identical samples, right, regardless of how you vary kind of the input's latent variable, right, just because kind of it's learning to ignore the input latent noise. Whereas in this case, you can see as we vary the different Zs, then we actually do get different samples. And so, this is, just to show you kind of where the model is most uncertain, right? So this is the mean, right? That's the mean over different samples that we generate, and this is the standard deviation that's over kind of these different samples. So you can see that this makes sense, right? So it's most uncertain about kind of the edge of the wings, right? Just because you can have kind of these various kind of plausible layouts of the dots, right? Without kind of impacting kind of how real kind of the image looks, right? So it is kind of most uncertain around kind of the edges of the wings and also kind of around these edges. Okay, so here's another example, taking a look at conditional image synthesis again. This is the task where you're trying to predict an image, right, from an input semantic segmentation map, right? So this is again kind of conditioned on the same input segmentation map, and then we're going to try to generate different samples, right? And so you can see that as we vary the input Zs, right, we were able to get kind of very diverse images, right? They are all consistent with the input image, but they vary kind of in the weather conditions or live conditions. Whereas for Pix-to-Pix HD, right, so that's a GAN model, and then so you, again, kind of you only see kind of one sample, right, just because mode collapse, right, even though this individual sample does look quite good. And so finally, well, not finally actually, but this is kind of the second, I think, third last example. So this is kind of looking at what the generative sample actually looks like, right, as we kind of do linear interpolations in the latent space. And the key thing to note here is that you have kind of smooth transitions, right, between the different points. And so here's another example, just looking at kind of whether the input, the learned latent space actually makes any sense. And so if you were to kind of sample different latent variables, but like feed in kind of different input images, you see kind of similar styles, right, across kind of these different inputs, right? So the same latent variable does tend to correspond to kind of a similar kind of rendering, right, of the scene. Finally, we can apply it in this interesting setting where we are fixing the Z, right? So the latent variable doesn't change at all, and we're just going to evolve, right, the input segmentation map, over time. So this is kind of the video that's generated, right, when you do something like that. For Pix-to-Pix, which is kind of based on GANs. So what you see here is that you see kind of lots of flickering, but each of the individual frames is actually quite good. And the reason why is because so it's kind of essentially at different frames, right? It's picking kind of arbitrary modes, right? There's no sense of continuity, right, across the different frames. Could be kind of collapsing to different modes, right, at different time sets. And so that's why kind of you see this sort of inconsistency. All right, so finally we have, so this is some follow-up work, right? Actually applying annually not to the pixels, right, but to the actual embeddings learned by a method called flow. And so this is kind of what that looks like, right? So you can see that if we were to do that, right, then you get good samples, right, and then you also get kind of good FID scores in this case, and then you also see kind of good samples of phases. So this is interpolating, right, between different phases, and so you can see the interpolations are also reasonable. And finally, I think this is the most interesting slide probably, right? So this is looking at the precision and recall, right, on two different data sets. And each of these points is actually one particular hyperparameter setting of a particular variant of a GAN or VAE, right? So the green points are the VAEs, the blue points are the GANs. And so there are 800 different plots in this picture. And so you can see that a single model, right, that's based on E is not able to outperform, right, these methods in terms of both recall and precision on these two data sets. Okay, and finally, just to recap, right, so we talked about three different methods, right, VAEs, GANs, and INLE, right, so VAEs require evaluation of the complete likelihood, right, so it maximizes the lower bound of the log likelihood. GANs, on the other hand, does not require computing the complete likelihood. And roughly speaking, it's minimized the reverse scale. And finally, for INLE, it doesn't require computing the complete likelihood and maximizes the lower bounds on the likelihood. And so that's it, right? That's the end of the lecture, and I'd be happy to take your questions. So not necessarily, right? So essentially this doesn't have this, repeat the question, right? So he was asking whether, this is more computation expensive than GAN because you need this kind of matching expense, essentially. Right. So basically, like whether it's more computation expensive because you have the updates right, on the parameters, right, data, and then you also have this matching stuff, right, that takes out kind of the generative samples, right, that each data sample is matched to. So in practice, it is not, and the reason why that is the case is because, like, remember, we don't have a discriminator here, right? So we don't actually need to train the discriminator. And also the second thing that we find is that it typically works if you were to use very stale matchings. So if you were to kind of compute the matching, right, between the real data and the generative samples, kind of, every, 1,000 steps or so, right, it's, reasonably, reasonably well. So that only has to be done very quickly. Directly on the latent space. No, okay, so it depends, okay, not on the latent space, but like it could be in some other space that's not necessarily related. This space is not parametric. Oh, okay, right. Yeah, so we don't have a model like that. So what I'm referring to is kind of you could basically, you can have some filtering in your net, for example, on top of the actual data, right, to compute features on the data and the samples, right? And then you can certainly impose a loss kind of in that space, right, defined by the pre-training loss, right? There is nothing that's actually, nothing that's learned kind of, concurrently, right, to your generator. You could do that if you want, right, but then kind of, you find that it's not. Yes. Yes. Sorry? What do I think is the way forward for adding temporal complexity? certainly, I think, yeah, so this would be kind of one step towards that direction, right? So having some sort of latent space that is actually capturing something, right, about the regularity across the different images, right? So that's certainly one step, right? You probably also would want to add kind of explicit losses, right? If you were to have like data, like actual video sequences, right? They can be used to supervise them, right? So I think that's definitely also something good to have, right? And then possibly like with a combination of those two ideas, that we probably would get like useful.
All right, awesome. Thanks so much.